מפאת האורחים אני אעבור לשפה האנגלית. Good morning, everybody. My name is Gabriel Motzkin. I'm the director of the Van Leer Jerusalem Institute, and my job in life is to open or greet conferences. I do several times a week, and I do it with, in this case, with great pleasure. When the people on the steering committee of the history and philosophy of science at the different universities came to me with this idea, I jumped on it because I thought this is one of the most important topics that we have addressed in my years as director. Now there's a price you have to pay for this. The price is you have to listen to me for 3 minutes, give the thoughts of a total layman on your subject. And so bear with me. Now what I'm going to say, I'm just going to raise a problem that strikes me, which is, as you all know, laws of physics are largely time invariant. The laws of biology are not. Moreover, you can think that information is not time invariant, that there's a deep relation between information and entropy, and therefore information is eventually all going to get lost. Now, the question is, where does this arise from? Because you would have to assume that you cannot get biology before you have information. So information has to be present before there is any biology. Otherwise, you would think that information only starts up with life, and that doesn't work at all. So this is all solvable, of course, if you assume that there's some divine perceiver out there and that the world is accessible to some meta-perception. But if you don't assume that, then you have a great mystery about the origin of not just the arrow of time, but of any kind of information out of the time invariant laws. Now, I've been reading lay books about this, and I have not yet found a solution. So maybe all of you can enlighten me on this topic, because I think that the origin of information is itself a topic worth addressing. So without further ado, thank you very much for coming. I'm going to be as much present as I can because I want to get enlightened. And without further ado, I'm going to ask Daniel Rohrlich. I guess you're the person who's speaking. Who's chairing the session? So you're going to take over. Okay, Rohrlich.
Our next speaker this morning is Daniel Rohrlich from Ben-Gurion University of the Negev from the Department of Physics. His research interests are the fundamental aspects and effects of quantum mechanics. For example, the axiomatic basis for quantum mechanics and retrocausality and beyond, in and beyond quantum mechanics. Daniel Rohrlich is the author of many papers in journals of physics on these topics, and in 2005 he published Quantum Paradoxes, Quantum Theory for the Perplexed with Yakir Aharonov. Daniel, please.
Thank you very much, Orly, and thank you to all of you and for the invitation to speak here, especially since I'm wondering what exactly I'm doing here. I'm feeling my way, and I think I will have something to say about information in the spirit of the talks so far today. And as a physicist, or as physicists go, I think I have a special openness to philosophy of physics. And yet, I think the connection today is more in the history of physics. Now, physicists are terrible historians of physics. In general, a physicist who will explain how a subject developed will tell you exactly how the subject should have developed. And the actual development was completely different. Except for one special situation, that's physicists who talk about developments that they've lived through, and seen close up firsthand. Those make excellent historians. So I was going to say that, you know, for once, as a great exception, I'll say something that's related to the history of physics. But then it occurred to me that that might be a sign of aging, that I want to talk about my experience in physics, in which case I can't promise that it won't happen again. because I'm only getting older despite my preference for retrocausal time-symmetric explanations. Okay. So I'll start with a bit of history, because thermodynamics, which is the part of history that I didn't live through, and it'll therefore be a very short summary. Thermodynamics gives us so much of an inspiration for understanding entanglement. Then I'll talk about entanglement specifically and how we measure it and why we are able to measure it at all. Measuring in the sense of quantifying it. So I'll start with Carnot. Carnot is an engineer, and he faced the problem of evaluating the efficiency of machines that he was working with. And Carnot found his way independently to the second law of thermodynamics, even before the first law had been stated. And you might say that the second law of thermodynamics says that hot and cold regions can't be created from an equilibrium without work. There may be statistical fluctuations, but the great average is that a thermodynamic equilibrium stays a thermodynamic equilibrium with uniform temperature unless work is performed on it. So in colloquial language, that's called, there's no such thing as a free lunch. And then Carnot considered this famous problem of two heat engines, and he made them reversible heat engines, and they operate between two different temperatures, T1 and T2. They both operate between those two temperatures. In order to get work out, you have to heat the system at one temperature, cool it at another temperature, and that yields some kind of some quantity of work. And he asked, well, suppose we have two of these machines, and one of them is more efficient than the other. That's what W greater than W prime greater than W means. It's more efficient, and in every other respect they're very similar. But if that's true, then since this one is outputting the same amount of heat as this one takes in, we can turn this machine into a refrigerator and have the energy that comes out of here go into there, and then we're left with an environment which is totally unchanged, because the same amount of work or heat, same amount of heat has been taken out of the environment and then released to the environment. We're back to exactly the same place we were before, but we have a free lunch because one of those machines gave more work than the other, and so we have that extra work, which is gratis. It's for free. We didn't do any additional work or change the environment so as to pay for this plus. That can't be. That violates the second law of thermodynamics, and from that, Carnot concluded that all reversible heat engines that work at between the same two temperatures must be equally efficient. And from reversible engines, it's a very short step to talk about all engines, because even if one of these engines worked only in one direction, we could take advantage of it to get that extra free lunch. So that's the lesson which is really going to inform the rest of my talk as we talk about entanglement. But I think it's also interesting to point out that this scientific work of Carnot cannot be classified either as pure research or applied research. He was interested in a practical question: how do I get the most efficient heat engine? But that question struck at the very heart of thermodynamics and led the way to a deep understanding of thermodynamics. So it's an interesting case in which we cannot make the distinction between pure and applied science, and that will also recur along the way. Now, this is less relevant, but I'll just mention quickly because it's not I'm not a specialist in thermodynamics, but it's worth noting that the ideas of thermodynamics have necessarily broadened over time. And that's interesting, that thermodynamics and information are closely related. So if we want to understand how the idea of information is broadening, then thermodynamics is also an inspiration. The first law of thermodynamics really tells us that energy is conserved, in particular that the sum of heat and work is conserved because heat is a form of energy and so is work. But the idea of conservation of energy is so precious to us that in many occasions where we could have said, well, so energy isn't conserved. We chose not to take that route, but to say, we'll define energy in a new way so that energy is still conserved. After all, this was all after Newton. Newton didn't formulate any conservation of energy law. But we do, and we couldn't imagine physics without it nowadays. So another generalization, the second law tells us that entropy can only increase. It can stay the same, but it cannot decrease. But now let's take some entropy and throw it into a black hole. Doesn't that look fun? I Googled impish smile, and this is what I got. Okay, so this is John Wheeler speaking. He says, this is obviously his idea. The idea that a black hole had no entropy troubled me, but I couldn't see any escape from this conclusion. So in his office, he remarked to Jakob Bekenstein that he feels like I feel like a criminal when I put a cup of hot tea next to a glass of iced tea and then let the two come to a common temperature, conserving energy but increasing the entropy. In other words, Wheeler had a real moral problem. He was accelerating the heat death of the universe, and there's no law against it, but it should be illegal. And that's a crime, he says to Jakob. But let a black hole swim by and let me drop the hot tea and the cold tea into it, then all evidence of an increase in the world, in the universe's entropy has been covered forever. This remark was all that Jakob needed. And it's very nice to remember this year when we no longer have Professor Bekenstein with us, what a brilliant student of Wheeler he was. Anyway, he proved, and I mean, this is a crisis for thermodynamics, because if you can get away, I mean, Wheeler was joking, but if you can get away with simply disappearing, I'm using it in the South American sense, disappearing entropy, then thermodynamics has a big gash in it. And Bekenstein thought, well, no, you can define entropy so that a black hole has entropy as well, and it's more entropy the larger the mass of the black hole. And he was using the fact that that Hawking had proved, namely that when two black holes collide, their total mass is always greater than the individual masses. And now we've heard it over LIGO. The total mass is greater. So that's like entropy. It can only increase. It can't get smaller. Now, so this was a lovely restoration of thermodynamics, but it too had a terrible flaw. Namely, black holes just swallow everything. They don't produce anything. You cannot say that a system is in thermodynamic equilibrium with the universe if it only swallows and doesn't produce. So the fact that black holes don't emit anything was a fatal flaw, actually, in Bekenstein's brilliant solution. And Hawking was he writes, I was very annoyed with Bekenstein for using my theorem about black hole masses in a way which didn't seem appropriate. So he wrote a paper against Bekenstein, but it continued to bother him until the point where it was actually Hawking who proved that black holes radiate. Black holes radiate black hole radiation. And so we have really a complete solution to Wheeler's problem. But I'm going to leave you with the following thought, because it bothers me as well. What this tells us is that thermodynamics and general relativity, which produces the black holes, together have a flaw. There's no consistent thermodynamics with general relativity and without quantum mechanics. With quantum mechanics, you can solve you can get a complete whole notion of thermodynamics, because quantum mechanics provides the black hole radiation. But it's very odd, and I say this just in passing because I don't know how to answer the question. It's very odd that we need quantum mechanics in order for general relativity and thermodynamics to coexist. That's not usually the case. Usually you can get some kind of consistency with, say, two theories without the third. Okay, so now I don't really have to explain this to you, but Bohr and Einstein debated quantum mechanics for years, and those debates had a resolution until the last issue, which they never could resolve between them. Is quantum mechanics complete or not? Here's the paper which presented it, the famous EPR paper. And it's a brilliant paper with no references. I'll mention it, I'll explain it briefly in the language of David Bohm, because that makes it much easier. Quantum mechanics allows us to measure the spin, the polarization or the spin angular momentum of a particle, but only on one axis. So here is a vector. That's all that we need to describe spin. We have a vector, but this vector is not on the x, y, or z axis. It's in its own direction, and it has components. Here's the z component, here's the y component, here's the x component of that vector. And quantum mechanics tells us that even though a particle has spin in some arbitrary direction, we can only measure one of these components, not all three. So that's a limitation, and that's where you would start to argue about whether quantum mechanics is telling us the whole story, or whether there's more that can be known, or at least must be accepted. But quantum mechanics allows us to put two particles together and check that their total spin is zero. The total angular momentum is zero. So now you can say, okay, I'll take one of those particles and measure its spin along one direction, one component. Take another particle and measure its spin along the other direction. And since the total spin is zero, I don't have to measure the two axes on the same particle, which anyway I can't do because of quantum mechanics. I can measure one on one particle and the other on the other particle, and I get all the information. Which is very clever and in some sense correct. And for Einstein, I think the crucial thing was that you can have these particles prepared in a state with total angular momentum zero. Take them far apart. I think it's changing. Be careful that when you transport them, their angular momentum doesn't change. Take them far apart. Make the measurements on them at the same time in some reference frame, so there's space-like separated measurement. So it's impossible, according to relativity theory, for one measurement to affect the other measurement. It's such a clean-cut thought experiment that it should work. Now, here are three reactions then and afterwards to the EPR argument. Bohr contented himself with proving that, although in principle this might be right, in practice you can't use this way to measure the two components of spin on the same particle, because when you measure on one even if you measure on them separately, at some point you'll have to bring them together, and the measurements may have spoiled the alignment between the measuring devices, so you can't rely on those measurements as in the same reference frame, which is fine. I mean, for Bohr's point of view, that's a crucial distinction, but Einstein wouldn't have cared too much because he believed that the thing exists and quantum mechanics doesn't tell us what it is, so quantum mechanics is incomplete. Pauli said something which I think is very unlike Pauli, but maybe I'm wrong. I didn't know him anyway. He thought the whole thing was what's called pilpul in Hebrew, or discussing how many angels can dance on the point of a needle, and that Einstein was simply barking up, was going the wrong direction. And then it was, so the most important thing about this slide is the time between, this is the year of the EPR paper, and this is the year of Bell's paper. That almost 30 years elapsed before anybody saw what Bell saw. Essentially, almost anybody. There was some slight progress. So, I mean, Bell's paper is one of the least technical papers I've read. Certainly, it could have been thought of before, but it wasn't. And probably because quantum mechanics was an exciting, developing theory, and people like Pauli didn't want to stop on what seemed like philosophical problems. Okay, for those of you who understand the notation, this is simply a singlet state of two photons, which we can use to generate correlations between the two photons, which will then be measured off in various ways by two experimenters, Alice and Bob, let's say, at different laboratories, and there'll be space-like separated measurements. The lesson to take from this slide is that the correlation between polarizations is simply the cosine of twice the angle between the polarizations. So when the polarization angles are the same, or the relative polarization angle is the same, theta is 0, so the cosine is 1. That means that the photons are required to display the same polarization if they're sent to the same polarizers, or polarizers with the same direction. But if those polarizers are 120 degrees apart in their orientations, then the cosine is minus a half. That means they're anti-correlated by minus a half. Okay? And if you just have that fact with you, the two correlations, the perfect correlation when Alice and Bob choose the same polarization direction, and the minus a half correlation whenever Alice and Bob choose different polarization axes, that's all you need to know to see what the real problem is. So here are Alice and Bob with their black boxes, and they measure these particles, which have these photons, which have some common source, and then they measure them, and they choose in ways that the photons obviously can't anticipate, but which of these three axes they're going to place in front of the oncoming photon. Now, suppose these photons are doing their best to do what quantum mechanics tells them to do. They say, okay, we'll have to draw up some plans that will teach us what to do under each circumstance. So they know that Alice and Bob might choose the same axis, and that axis might be the 0 axis, it might be the 120 degree axis, it might be the minus 120 degree axis. Yeah. So they could both choose this one, or this one, or they could choose different ones. So in case they choose the same one, the photons have to be prepared to give the same answer. They have to, because quantum mechanics leaves no room, or very little room for error here. Now, suppose they all said no. We won't, no in this case, by the way, means they don't pass through the polarizer. Yes means they do pass through the polarizer. So they could say no to everything. They simply agree from the start. give us a polarizer, we won't go through. Fine. But then not only will their same axis correlations be 1, so will their different axis correlations, different polarization axes be 1. Everything will be correlated. Either both photons will go through anything, or they won't go through anything. That's not minus a half polarization. Minus a half correlation. But even if they do better by saying, okay, these two will say both yes, and these two will say both no for this and for this, that adds up to a correlation of minus a third. They're not doing as well as quantum mechanics, which does minus a half. But nothing can make it go better than this, because that's all they have. They can either disagree on 2 and agree on 1, or they can agree on 2 and disagree on 1. Being here they disagree, and here they disagree, and here they disagree, but here they agree, and that's the best they can do. So there's no way these photons can be equipped with instruction sheets telling them how to behave, and so there's no explanation in local terms why quantum mechanical correlations are what they are. It just doesn't make sense. And I think this is Bell's comment here is an answer to Pauli, namely that Einstein had it right. He really was looking for the right thing, and it's a pity that it doesn't work. Now, my reaction to this question was the correct response is to beat your head against the wall for as long as it takes. And then when you've stopped beating your head against the wall, well, what do you do next? I was inspired by the saying of Lord Kelvin that if you can measure something, then you know something about it. So, okay, forget about trying to understand quantum correlations, but maybe we could say quantify them, put some handle on them that would make it something that we'd say we knew. So, for example, is a state like this, which is a singlet, which gives us those perfect correlations on the same axis that we saw, is that more, that's entangled, right? It's entangled because we can't factor the wave functions of the individual photons into a product. But is it more entangled than this one? Like this one is mostly this and just a tiny bit of that, and if we got rid of that, who would know, and then it wouldn't be entangled anymore. So it looks like this one is more entangled. And we actually were able to prove a number of things. For example, that this one you can't mix any product states into that. If you had some of these pairs, some of these photons in product states, you would detect them. Whereas if you're in this state, you could take some of these states and mix some unentangled photons, and then you would be able to get by without being detected. So that makes, in some sense, this is more entangled than this one. Okay, but that's a lot of hot air, because we really don't know. I mean, in some sense it is, but it's not a measure of how entangled. So now comes the part which should remind you of Carnot. Entanglement is useful. It's useful in a weird way. I remember in the 90s when I was a graduate student, and I was in the 80s already. Well, I was a graduate student, and I read this paper of Charles you know the guys. Bennett and some collaborators. And they showed how you can use entanglement to teleport a particle state, not the particle itself, but teleport a state at a great distance. And I thought, this is so weird. Why did this get published in Physical Review Letters? Who would want to do such a thing? It's still off the wall. But Physical Review Letters has a certain receptiveness to practical things, even if they're totally impractical, but in some sense you can do something with it. And and in retrospect, of course, I have to totally agree with Physical Review Letters for publishing that article, because it really was visionary. And then there's quantum cryptography, which might be more also familiar to you, and distributed quantum computing, which is very powerful and is still to come. So, teleportation, we're going to approximate Captain Kirk by qubit in an unknown state in Alice's laboratory. So, this is the state of Captain Kirk. This is an entangled pair, an E-bit, namely a maximally entangled pair that Alice and Bob share. Alice makes one measurement projecting onto this state, which is one of the Bell states. And then Bob's qubit is left in the same state as Kirk was originally in. So Kirk's state has been transferred from Alice to Bob. No longer exists at Alice's place, it exists only in Bob's place. And I've made it sound a little bit simpler than it is, but this is actually dangerous because it would mean that it could all be done instantaneously. But in fact, there are 3 other possibilities, and Alice has to send Bob a tiny bit of information so that he can know which one of those possibilities is realized, and then he has to either accept the state that he has left as Captain Kirk, or he has to just do a little rotation or something like that to get Kirk. So that's teleportation. With quantum cryptography, and I'll just say that if you have things that are perfectly correlated and nobody has any access except those who do the measurements, then one thing that you can get from them is a long string of zeros and ones. Right? So let's say they have all these represent photons. This here represents a series of outcomes from measurements on photons. It's just simply a random sequence. But Alice and Bob are the only ones who have this sequence because they're the ones with the photons. And now Bob says, this is what I want to say to Alice. All I do is subtract from it this common sequence of random ones and zeros. And then I'm left with a sequence which I can simply layer over, whatever microphone is available or send by uninsured post or whatever. I can advertise it in Haaretz. When Alice gets the message here, she adds on what I subtracted, and then she knows exactly what I had to read. And this code is unbreakable because only Alice and Bob have access to the random string. Of course, it's a one-time pad because you can only do this once, but you can keep generating this all the time. And then there's quantum computation, which is based on a quantum computer, namely a computer that uses qubits superposed ones and zeros instead of classical bits, which are true ones or zeros. And there's some terrible irony of history. I mean, there's something unbelievable. Namely, the kind of problem that this quantum computer, certainly going to be hard to build one, but the kind of thing that this one can do is factor huge numbers into huge primes. So you take 2 10-digit primes and multiply them together, you get a 20-digit number. It's hard for a classical computer. It's very, very hard for our computers to break that, to factorize that product. And the kind of cryptography that is in use today in banks and governments and so on is based on the fact that it's hard to factorize those numbers. So I'm sure there are a lot of people in a lot of places high up in secret who are very worried about the possibility of their codes being broken on a quantum computer. But not to worry. First of all, the largest number that's been factored on a quantum computer is only 6 digits long, so we've still got a few weeks, maybe months. And if we want unbreakable codes, well, quantum mechanics gives us an unbreakable code. Just get on those qubits, use entanglement to encrypt your communications, and you'll all be fine. So this is what we say in Hebrew. Baruch Hashem asher akdim trufa lemaka. God or nature has provided us with the answer to the upcoming disaster, the response to the upcoming danger. Okay, so now, armed with 3 applications of entanglement, we go back to the question of measuring, or rather quantifying, entanglement. Now, we're going to stay with the simplest possible entangled pair, just as before, the up and down entangled bits shared by Alice and Bob. And now, we're going to say, what's the relationship between a qubit like this, which has unequal probabilities, right? Before, we conjectured that when p is equal to a half, so that 1 minus p is also a half, that's the most entangled one, and then any other choice of numbers would make it less entangled. But now we can actually do something. This is the paper I referred to before, Bennett, Bernstein, Popescu, and Schumacher. And they showed that you can take, I'm going to call them weaker. This is a weaker form of entanglement, although I haven't proved that, but the proof is just about to come. So it would be convenient to call it weaker. So you can take k of these less entangled pairs and convert them into a number n of perfectly entangled pair. In other words, pairs with p equal to a half, which are also called E-bits, or maximally entangled states. You can do that with you can't do it very well for a finite number, but in the limit of asymptotically many pairs, you can do that with an efficiency which is the von Neumann entropy. This is how well you can do it. So obviously n has to be smaller than k, because if you have more entangled pairs, less entangled pairs, and you concentrate the entanglement, then you're going to get fewer pairs, but each one is more entangled than before. Now, so the entropy entanglement seems to be a way of measuring entanglement. But how do we prove that it's a measure of entanglement? Well, we go back to that analogy with the Carnot cycle. We say, just as nature does not allow hot to move away from cold and produce non-thermal equilibrium without work, in nature we cannot produce entanglement without actually bringing material from Alice to Bob. Alice and Bob in their own laboratories cannot increase or create entanglement. That's almost self-evident, so I won't go through the proof. So there should be no way of producing entanglement at a distance. There are all sorts of ways of trading entanglement, transferring entanglement, but ex nihilo creation of entanglement doesn't exist. So that's a law of quantum mechanics. Alice and Bob can certainly destroy entanglement very easily, but they can't create it at a distance. So let's take 2 of these reversible. I didn't say, but the crucial point is that you can reverse these. Well, I sort of did say that. You can reverse this process. You can dilute single E-bits into less entangled pairs, or you can concentrate less entangled pairs into E-bits, fully entangled pairs. So let's do that. We have a certain number of entangled pairs that go in of the less entangled type, and we take E-bits out. And we can have another machine which does it even better. It produces n prime E-bits that is better than the n of the other machine. But of course, you know what we're going to do. We're going to feed the output. We're going to reverse this machine and feed the output into this machine. So we start out with n E-bits. We put them through the machine. We get k pairs out, which we then insert into this machine, getting more E-bits out than we started with. And that's a free lunch. And as you know, nature doesn't free lunch. So that's impossible. So that means that we have a rigorous characterization of the amount of entanglement in a certain number of pairs. Now, the thermodynamical analog is not yet exhausted, because you could say the more, you can say, yes, these pairs are entangled, the more coefficients of the superposition are equal. But that only tells you that it's that kind is better than this kind, but how do we actually put a number on entanglement? For example, we could say entanglement of these k less entangled pairs is measured by how many ebits they reduce to. So if the k pairs reduce to n ebits, then we'll say they have amount n of entanglement. But how do we know it's n? Well, it could be n squared, n cubed, e to the n. All these are numbers which characterize and differentiate between the k and between the less and the more entangled pairs. Well, actually, that's not allowed, because you can only do this in the limit of infinitely many pairs. Only in that limit is this conversion exact. And so we're dealing with what in thermodynamics is called an intensive quantity. It's not something which we can talk about the total entanglement. We can only talk about the average entanglement per particle. And if we do that, then the only thing which has a limit is k over n, not k squared over n or e to the k over n. Only the limit k over n, only the fraction k over n has a thermodynamic limit in this case. And therefore, the only measure of entanglement is proportional to this n, or the k over n. Unfortunately, I can't tell you where to go from that, except, or in a sense I can, because I think there's a lot more to be done, and I haven't seen it done. Maybe it's anyway. What's the connection of this measure of entanglement to thermodynamics, apart from the analogy? Well, I'll tell you. The connection is that Sando had to leave his apartment because he was going to Europe for a postdoc. And he had to move things out of his apartment to a friend's apartment, including a refrigerator. So the two of us were pushing this refrigerator along, and Sando was telling me about this way of converting e-bits into less bits and so on. And even you can go back, but he doesn't know if it's the most efficient. I said, Sando, don't your ears hear what your mouth is saying? If it's reversible, that is the most efficient conversion that's possible. So we were at this table. I think that we can say a little bit, that's the true connection, but I think one can say a little bit more. Namely, there's something very special about entanglement. Entanglement, when you look at it locally, looks like entropy. You don't know that this state here is perfectly correlated with that state there. So all you see locally is a density matrix. And there's even a very nice work on the origins, the foundations of thermodynamics, which began with a brilliant idea of Yakir's, which he never pursued, I guess, and was developed many years later by Sandro Popesco and Short and Winter, saying that essentially you don't need a subjective description of probability in thermodynamics. Because suppose you start out with an entangled state, but it's in one place. It's one place and it's a pure state, and that state is entangled. But in the nature of things, things in the universe tend to move around. So one of these entangled systems will move over there, and the other will move over here, and pretty soon we'll obviously have lost track of what's entangled with what. And to us, locally, they just look like density matrices. So you have a perfectly good explanation why the total entropy of the universe could be zero, but there's entropy all around us everywhere. So I think that once we talk about measuring entanglement, that we have to bring in thermodynamics not only as an energy, not only as an analogy, but also as part of the discussion. I'm going to conclude, as you see, but with a comment, namely, hearing the discussion this morning and not having thought about it much before, I'd like to take a boring position and say that information is, after all, what human beings transfer to other human beings. What happens along the way, is very interesting, but I think that we can extricate ourselves from the complications of defining what quantum information is if we say that, it's another means, and it's quantum information because quantum devices are essential to it, but we don't have to worry too much about defining it. But of course, it's certainly a revolution in how we have to think about information. Thank you very much.
Thank you very much, Daniel. Let's take questions, comments. Yes? The microphone, please.
Thank you for the talk. I would like to begin with your final claim that information is everything that human beings transfer to other human beings, and I think that we have to take care about that. I can give you a receipt of a pie, to make a pie, and this is a kind of information that I give you, but if I give you the pie, it's completely different. So there is something more that we have to take.
Why should that be the same kind of information? It's not, so, I would agree they're completely different, but I would say that both are examples of information.
Well, I do different things with the receipt and with the pie. I mean, I can do something again, I can repeat the pie with the receipt. So there is an information there to make something. With the pie, I can only eat it. So, well, okay, this is my point. Perhaps we do not agree, but I think that there is some difference. Not everything we transfer can be think as information. You have to make a complete context to be thought as information, a pie, for instance. And, well, this is a consideration. And the other is about entanglement, that it's very interesting, your analogy, or well, you try to make more than analogy between entanglement and thermodynamics. But the fact is, I think that there is even another analogy, because entanglement is relative to the partition of a system in part. You can have many systems interacting, and you have different tensor product partitions, and you have different kind of entanglement between them. And perhaps when you are thinking about entropy in a system classically, you can think the same. Depends on which kind of observables you are considering. You are measuring different kinds of different entropies. I mean,
I didn't emphasize it, but I did mention it in this previous slide. It's very hard to generalize this result to all entangled states, because there's just so many different ways to entangle states. So this is totally restricted to the bipartite case. And even in that particular bipartite case, it's not. It's only restricted to pure states. So there's this is scratching the surface, but I think in an interesting way. You couldn't do this in some other
Please, other comments or questions? Can I, yeah. So can I ask you something? You were talking, when you're making this analogy between the quantum case and thermodynamics, I think one important difference between them, and I'm wondering about what you think about this difference, is that the case of quantum mechanics is a case of a fundamental theory. It's not only a case of an effective phenomenon that you see at the observable level, where I use the term observable in the intuitive classical sense of the term. And nobody thinks that, I think so, that thermodynamics is a fundamental theory, and in fact, there are still attempts to prove the second law of thermodynamics from fundamental physics. I believe that these attempts are doomed, but the project is ongoing, and it's ongoing because thermodynamics is not a fundamental theory. So perhaps this analogy may be significant for your project.
It's a very interesting distinction. My first reaction is that when you're talking about using entanglement and about measuring it, you're in a realm which is, again, the question is not pure science or applied science. You're in a realm where you're using lots of these things. I think that it's true that quantum mechanics is a fundamental theory, but I think that quantum entanglement, properly understood, at least when we raise it to the numbers of amounts of entanglement and numbers of entangled systems, that makes it useful for quantum information. It's already turning into a branch of thermodynamics, and that's what I'm suggesting here at the end.
Okay, well, perhaps just if nobody else wants to, so I'll use this opportunity, because if you're using thermodynamics as a serious analogy, then you surely assume that the second law of thermodynamics is proven, or at least provable, to take it so seriously to the fundamental level and explain of that, and as a useful tool for working in the domain in which you're interested. And my hunch is, or not only hunch, I believe that the second law of thermodynamics is in fact not a theorem of mechanics, and there are counterexamples, varieties of Maxwell's demon. So the second law is not a law in that sense. It is an effective law in very interesting cases, but it's not fundamental. So to take it to quantum mechanics is perhaps a bit more dubious.
That's also a very good point. You can't create entanglement at all. It doesn't happen spontaneously. Oh, once in a while you get a bit, until you get to the level of quantum field theory. At the level of quantum field theory, I think there might be kind of zero-point creation of entanglement, because you have these particle pairs popping out of the vacuum, and there's even work. It's not my work, but there's work by, for example, Benny Resnick and others about so-called harvesting entanglement from the vacuum. So there might be something more like what you described.
Yes, please. May I just one last question?
Well, this is just a comment. I wonder what you think about it. There are some results from quantum mechanics that are related to Carnot's efficiency limit. I'm referring to the work of Scully and his collaborators, and where they seem to, they have the idea that you can use quantum, what they call quantum coherence, in a way that will allow to extract work from a single heat bath. So that's going to, and that is usually taken to violate Carnot's principle. And as far as I can see, there is no, they don't rely on entanglement or anything like that. Just on the superposition, the quantum mechanical superpositions. Do you have any way of connecting these issues to what you're doing?
I'm totally ignorant. I plead ignorance. I don't know this work of Scully's. I don't know about it.
So we'll send you the paper. It's very interesting in this context. So join me in thanking the speaker.